Hi, so this is our 16th exploration of Sylow's theorem. So we're saying this is Sylow's theorem, and this is part 16 of our exploration of this theorem. Now, Sylow's theorem just says that suppose there's some group G whose order is p to the alpha times m, where p and m are relatively prime. Uh, does this guarantee us? Does this guarantee us that there exists some subgroup H of G such that order of H equals to p to the alpha? Right. So we're not sure about this. So far we appear to have established that in the case when G is cyclic, the statement is true. And now what's really seems to be the issue is figuring out, well, what if G is not cyclic? Right. This seems to be what we're thinking about now, is what if G is not cyclic, right? And suppose that order of G is actually still p to the alpha times m. Is it necessarily true that there exists some subgroup H of G such that order of H equals to p to the alpha? So the tactic we've been trying to pursue so far, we're not sure if it's going to work or not, but the idea was, it's turning out not to be too easy to prove this, but it turns out that we saw last time that perhaps if instead we showed that if G is not cyclic and order of G equals to p to the alpha times m, and that the following is true, that is, we have some element of the big group, we have some element little g in G such that order of little g equals to p to the alpha times L, where L is some divisor of M. Apparently, we seem to be saying that if G is not cyclic and order of G equals p to the alpha times M, if these two statements imply that there is some element in the group whose order is p to the alpha times L, that appears to be again sufficient to prove the case when G is not cyclic. But this still begs the question: how can we prove that there's an element G in G? There's an element little g in G whose order is p to the alpha times L, right? How do we know this? So at the moment we're actually genuinely confused. We don't know. And before we're pursuing this strategy, we're considering a set. We're not sure how it will come into play here, but it appears that in proving that when G is cyclic, the theorem is true, we didn't really use the fact that the GCD of P and M is 1, that they're relatively prime. So perhaps it's going to be of value to us here. And the strategy we were looking at before was, well, let's consider the set B, right? So we're saying that let's suppose that the conclusion is false. That is that actually there is no element, right? That means that aren't we saying that for all little g in G, let's suppose that for all little g in G, uh, it is true that this is supposed to be a comma. It is true that order of G equals to never equals to p to the alpha times L. Okay, that is, the power of p is always something less than alpha. Okay, so what? If we can obtain a contradiction here, wouldn't that mean that actually there must be some g such that order of g equals to p to the alpha times L? Right? So perhaps contradiction will help us, but we're not sure yet. So the strategy we've been using is to study some set called B, and we're saying that, well, just let B be the set of all p to the I times L. Right. Here p to the I times L is being taken to be some divisor of p to the alpha times M, such that either I is less than alpha strictly, or L is less than M. Right. So this set here would in this set be telling us that we're saying that doesn't this set B contain all the possible orders that elements of G can have? Given that if we're supposing that, well, none of them has order P to the alpha times L, and we're saying that either the power of P is less than, right, so let's put it this way. Well, it's pretty clear that if we had some element little g in G whose order was just P to the alpha times M, would be done, right? Wouldn't this show us that there must exist an element of order P to the alpha, right? Because it's an M a divisor of M. And we said that we seem to be saying that for the case when order of G equals P to the alpha times any divisor of L, we're done. So we may as well suppose that we have no divisors. We may as well suppose that we have no divisors. There's no element little g in G whose order is P to the alpha times M, right? In which particular case then our set B of all possible orders must be designed in such a way that well, it's strictly less than P to the alpha times M. And isn't that the same as saying that the value of L is either going to be less than M or the value of I is going to be less than alpha for whatever P to the I times L is being taken to be a divisor of P to the alpha times M. Yeah, but again, this still begs the same question, so what? Sure, we have the set of all possible orders of elements of G, but why is that important to us? So one thing we think was maybe we could obtain a contradiction, because we know that by design, and we're saying that P to the alpha times M is not in B. Right? P to the alpha times M is not in the set of all possible orders of subgroups or of elements of G. So we're saying that P to the alpha times M is not in B. So perhaps we can prove that P to the alpha times M is in B, which would be a contradiction. But again, it's unclear how this contradiction is going to work. But you know, if we're assuming that the conclusion is not true, that we never have P to the alpha times L, can't we say more? Can't we say that, well, we're considering the set B which equals to, I don't know, P to the alpha times L1? No. That is, no, aren't we saying that the elements P to the alpha times L1, L1 is some divisor of M, P to the alpha times L2, P to the alpha times L3, all the way up till P to the alpha times LD, where D is the number of divisors of M. Okay? And we're saying that if we're saying that there is no element of order P to the alpha times L, and we're saying that none of this set here, call it X or whatever, this set X of P to the alpha times some divisor, well, this set is not one of the possibilities. That is, no element has any of these orders. P to the alpha 1, L1, P to the alpha L2, P to the alpha L3, up to P to the alpha LD. So then, really our set of possible, then our set B of possible divisors can be restricted even more. Can't we say that it's the set of all P to the I times L such that Well, I is less than alpha, less than or equal to 0. Um, right, just that. Right. And then we just know that L is some divisor of M. Right. So, is there anything again bizarre about such a set? Is there any reason why it's contradictory? It's unclear. So this again, this problem here, this approach seems to just be leaving us with many mysteries. Um, so maybe looking at the set of all possible divisors of p to the alpha times L may not be necessarily the way to go. But the question still becomes, how else can we show that there's an element of the group whose order is p to the alpha times L? Well, another question is, can we construct an element whose order is definitely p to the alpha times L? Yeah, that's also unclear how to do that. How are we going to find an element in the group whose order is p to the alpha times L? Given that the group is arbitrary, we don't know what elements are in it. All we know is that the order of the group is p to the alpha times m. Again, it appears that the thing that's really messing with us here is that we're not really sure what the consequences are of p and m being relatively prime. Why is that so clear? Why is that so important? It's unclear. That is this fact that p and m are relatively prime. Okay. Right. Well, what else can we deduce from that? We deduced a bunch of stuff before, but maybe something new. Hmm. All right. We did the obvious before. We said M is an element of Z mod PZ star, um, and P is an element of the set of all. We said P was an element of Z mod MZ star. So what? But here we're dealing with powers and orders. Um, yeah, this is really weird. Okay, maybe no, this is a bizarre idea, but well, okay, sure. So we have a group, and we know its order is p to the alpha times m. Okay. Now, question. Well, sure. Suppose that for all g and g, for all g and g, order of little g never equals to p to the alpha times m. Okay, never equals to p to the alpha times m. Okay, that's all well and good. But since order of g divides p to the alpha times m, we know that, can't we say that, and the group is finite, can't we say that there exists some maximum, let's call it g star, little g star element of g, such that, well, order of g star is some p to the j times L, where this p to the j times L is the largest order that an element of the group can have. Alright, we just run out of time, but we'll try and pursue this order of having the element with the largest order in the group and see if maybe we could show that the element of the largest order has to be of the form p to the alpha times L, right? Because one question is, what possible the question could be, if we're looking for things of the form p to the alpha times L, elements of the group of the form p to the alpha times L, what kind of elements of the group are going to be candidates to be elements whose order is p to the alpha times L? Could it be that maybe the element in the group whose order is the maximum is going to have the form p to the alpha times L? So let's evaluate this. Bizarre idea just came up now, kind of like the maximum order element of the group. Maybe that will give us something. If not, well, we'll just abandon this approach and try something else. Thank you very much for watching this video, and have a relentless week. Bye.